Well, and coming to the ATS Friday today. And today we're lucky to have Nicholas Scarsdale. This is from UC Santa Cruz, where he's a graduate student. So Nicholas was enormously helpful in the JWST early release science program, where we were working with and the enormous pile of data that came in. So thank you for helping with all of that. And then today we're going to be hearing about really cool, exciting stuff studying smaller planets with JWST today. And so Nicholas works with I think the Battaglia science family, including both Natalie Capella, who helped run the Kepler mission, led the JRS program, and then also Natasha Capella, who at least some of them. Yes. Take it.
Awesome. All right. So Zach, thank you so much for the great introduction. So I am going to be presenting about kind of a variety of things I've done over the course of my thesis. You could view this as sort of a Frankenstein's monster, or perhaps more positively, a bit of a Voltron of subjects that hopefully I will convince you combine together to make progress on our understanding of small exoplanets. So if I can change my slide. So I'm in the Zoom share. I can't like click in the shared screen. So I'm tapping slideshow with no success. Let's see. Okay, hold on. I'm going to stop sharing again. So we can do this, and then if I share this. We did it. Okay, hooray. Great news. Okay. So as a brief outline, I'm going to be giving a little bit of background on small exoplanets, just so we have a shared context going forward. I'll talk about characterization with JWST, starting with the early release science program, which, as Zach alluded to, we had this big pile of data with all the instruments on a single target. And then I'll talk about the COMPASS program, which is Natasha, Battaglia, and Johanna Teskey's Cycle 1 program that I've been lucky enough to work with. I'll talk about some supplementary efforts related to planet discovery. And then finally, I'll talk about some more detailed atmospheric modeling I've been working on, trying to discern between rotation regimes via atmospheric observations. So small exoplanets is a bit of a weasel word. Small could mean many things. So specifically what I mean is planets between the size of Earth and Neptune. We don't have any solar system analogs for planets like this. And it turns out they're actually very numerous. So it's a bit of a joke that exoplanet astronomers are obliged to show the period radius diagram from Kepler at the beginning of all their talks. I'm showing a slightly modified version of that diagram. So rather than just showing the planetary detections, I'm showing the actual underlying occurrence. So this is not just how many planets we've seen, which is confounded by a variety of observability and instrumental effects. This is what we think the actual number of planets per star is. And this is from my wonderful colleague, Ann Datillo, who has done a lot of work on Kepler occurrence. And so you can see that in, I guess the Zoom people won't be able to see me point, but the regime where planets are most common is in this between 1 and 3 Earth radii. So even though we don't have them in the solar system, we know they're very intrinsically common. Furthermore, from measuring their masses, we know that their compositions are very diverse. So here is, rather than period radius, we're showing mass radius. This is a plot that another member of Natalie's group, it's a bit of a core of some of the work that Natalie's group does. This is from Joey Economurphy, who is a radial velocity expert and does a lot of mass measurement and mass radius plane characterization. So this is just a plot of discovered exoplanets with measured masses. The underlying kernel density estimate is plotted in gray, so you can kind of see the radius valley, this gap between planets that sort of cluster around Earth-like compositions, the super Earths, and planets with a wider range of compositions. So importantly, these sub-Neptunes up at about 2.5 Earth radii, their compositions aren't just diverse, they're also degenerate. So if you look at, for example, the plus 5% hydrogen helium and the 100% water lines, 100% water might not be the most physically motivated composition, but just as an example, you can see that this silicate plus a few percent mass in hydrogen helium is completely degenerate with a water composition, even for arbitrarily precise masses and radii, which we never have. We need a way to, if we want to understand the structure and composition of these planets, we need a way to break the degeneracy in mass radius space. So this is kind of a common refrain, and it is true, but the kind of details of what our actual needs are for breaking this degeneracy, I think could use a little bit of elucidation. So this is something I'm extremely interested in working on in my postdoc, which hopefully somebody will hire me in the next 6 months. And I think a lot of my work so far in grad school kind of circles around and builds up to this theme of understanding what do we actually need to understand the structure and composition of the sub-Neptunes. So to start off, I'll talk about some atmospheric observation, very clean transition. And I'll open with the early release science program. So in principle, this should be easy mode, right? We have a hot Jupiter, so the transmission spectrum features are very large. It's a puffy hydrogen helium, primarily atmosphere. We have this gorgeous panchromatic spectrum from 0.5 all the way up to 12 microns with every JWST instrument. There's plenty of overlap, so we can characterize the offsets between the instruments really well. So, the idea is this is like could be the gold standard for characterizing exoplanet atmospheres. It turns out that the free retrieval abundances, when we go to characterize the content of this atmosphere, actually have some dispersion. This is a plot or a version of a plot that's going to be in the early release model synthesis paper, which will come out soon, I promise. We've been working on it for a very long time, and Luis just got a faculty job, so I think he's been a little busy. So this is just showing 3 of the different free retrievals, the posteriors, and C/O ratio and metallicity. And you can see that the 1 sigma contours, they don't actually overlap with each other. And so this is for Aurora and Chimera, which are 2 other codes, and then Picasso, which was the code I was in charge of for the model synthesis project. So I won't talk that much more about this since my presentation is about the small planets, but this just kind of foreshadows the level of difficulty of characterizing atmospheres in really extreme detail, and the challenges will only be magnified when we go to the small planets. So on that note, the COMPASS program, which stands for Compositions of Many Planet Atmospheres for Statistical Study, this is a quantitatively selected set of planet atmospheres. And the reason for the quantitative selection function is that this enables population level inference in a way that is not enabled by picking planets just sort of based on vibe. So the quantitative selection function, in principle, once we have all of our data, will enable us to do a population level analysis. So the core idea of the COMPASS program is to probe the radius valley, which, remember, is this gap between these seemingly rocky and seemingly volatile rich planets. So we want to probe across the radius gap to understand whether we're seeing, for example, a transition from primary atmospheres and the larger planets to secondary atmospheres and the smaller planets. I have a link to our website here if people are interested in checking us out. So here's the sample. The most important characteristic of the sample probably is just, here's the quantitative selection function, and the weighting with a normal distribution centered at 1.7 Earth radii, which is the radius valley approximately, is kind of the key characteristic, that it's sort of centered to straddle the radius valley so that we can understand if we're seeing a transition from maybe primary atmospheres up here to secondary or perhaps no atmospheres here. Internally, we refer to the planets by their TOI numbers, which can be very confusing. So for those of you who might know the alphabet soup names of the other planets, some of these might be more familiar to you by their alphabet soup names, not their TOI numbers. So like LTT 1445, L9859, just in case you have a terminal exoplanet brain and have all these alphabet soup numbers at hand. So far, let's see. Okay, well, I'll just ignore it. I was going to try to hide this. Oh no. There we go. Okay, put it over there. Oh no. Okay, I'm going to do this tedious slideshow thing again, just so that people don't have to see something horrible on Zoom. Apologies for all of these tech issues. Yeah, should have anticipated. I should have known this would happen. Linux, my old enemy. Okay, so we're back. And hopefully, okay, great. These are the spectra from COMPASS that are public so far. There's actually only 4 of our 11 targets. Others are sort of submitted, or we're just finishing up the analysis, but I've just included the public ones here just for, I mean, I don't think any of you guys are going to steal our data or anything, but just out of habit. All of these spectra are unfortunately flat. And you might be saying, I don't know, some of these look like they might not be flat. And I'd love to talk in a little bit more detail if people have questions about kind of the methods we've been using to quantify flatness. But for now, I'll just say that we think that all of these spectra don't show strong evidence for molecular absorption.
What about the CO2 4.3 micron?
What about it? So for this planet in particular, there's a lot of scatter in the transmission spectrum you can see. This is also a, I think, 1200 Kelvin equilibrium temperature, like rocky planet. So we really don't expect it to have much of an atmosphere. The error bars here turn out to be such that there isn't significant evidence for an absorption feature in the CO2 bandpass. It's also slightly too red. And that's true, like for this one, right? We kind of were thinking like, maybe this is really a feature, but for a variety of reasons, we don't think it's molecular absorption. And I'd love to talk more about that at the end. So to zoom in on one of our targets, this is the top one up here. This is L9859C. This is the target that internally we call the paper leads champions. So I was the champion for this target. This is a warm super Earth. So it's clearly on the kind of super Earth, maybe rocky, maybe secondary atmosphere side of the radius valley. Here are our 2 spectra from 2 different visits. I've shown them reduced to 2 different pipelines so that you can feel confident that our results are robust against different reduction techniques. And both of these, when we first got them, you can kind of trick yourself by eye into maybe thinking there's some wavelength dependent variation here. But it turns out that the best fit model for the combined spectrum is no features at all. One of the best ways to see this is just the chi-square values. So no atmosphere is this dashed gray line. You can see that fits really well. There are plenty of scenarios that are also decent fits, like a clear CO2 atmosphere or a clear water atmosphere. These are pure CO2, pure water atmospheres. So we certainly are not asserting conclusively that the planet has no atmosphere based on its transmission spectrum. But again, we don't have strong evidence for molecular absorption. What we can do is still put useful constraints on this atmosphere. So in these plots, what I'm showing is a parameter space sweep. Keep awkwardly shuffling my chair. So I'm showing this sweep that we do where we have on the x-axis atmospheric metallicity relative to the solar value, or if you prefer, the mean molecular weight, depending on whether you think metallicity is a good way to parameterize atmospheres that might be secondary. And then on the y-axis, we have just the opaque pressure level. So this could be a thick cloud deck, or it could be the planetary surface. So, you know, at 1 millibar, this could be an atmosphere with a thick cloud deck at 1 millibar, or it could be a planet whose base pressure is 1 millibar. And so the 3 sigma confidence interval is shown with this white line. So except for really, really high altitude clouds, we do rule out atmospheres more metal rich than about 300 times solar. Again, kind of thinking about the potential for these atmospheres to be secondary, we've also experimented with just H2CO2 and H2H2O mixtures. And in these cases, we get similar constraints in terms of mean molecular weight, a little bit better for CO2 because it has this huge feature at 4.4 microns, a little bit worse for water because the water opacity in the 3 to 5 micron bandpass is kind of, you get like the shoulder of the feature at 2.7 microns, but it's mostly contributing to the continuum. So our water constraint is a little bit weaker, our CO2 constraint is a little bit stronger, but in general, we're ruling out atmospheres heavier than around mu equals 10. So, yes.
Okay, if I interrupt you.
Yes, feel free to jump in. Yeah, I'm happy to chat live.
So I was hoping, and some of us have spent a lot of time with transmission spectra, but maybe some of us haven't.
Okay.
So I was wondering if you could give a brief, like, explanation of what is the transmission spectrum you're measuring, and like why does mean molecular weight matter for
Got it. Yes.
If that would.
Yes, happy to. So basically, when the planet transits the star, you can see a dip in the host star's brightness. And if you look at the wavelength dependence of that dip, I'll go back to the WST39 example because it's way prettier. You can infer that modulo, like maybe weird stuff going on with the star, which I won't really talk about in this talk, but just so that you know, I'm not being overconfident. There are issues here, but in general, you can, assuming that you feel confident that it's not some weird star stuff, you can assert that this wavelength dependent variation is happening because there's an annulus of planet atmosphere through which the starlight is passing and causing molecular absorption. So for WST39, we have these really nice, strong CO2 and water, and then maybe not as nice, but still kind of nice SO2 features. And so the wavelength dependent variation of the planet passing in front of the star, we attribute to the planet atmosphere. Sorry, I have been giving this talk to like more exoplanet focused people. So if there's ever like a, whoa, what is that jargon? Or like, what did that guy just say? Definitely don't hesitate to jump in. I'm really happy to like give a slightly deeper explanation of what I'm working on. Okay. So, oh, and you asked why the metallicity matters. So, because you have this annulus around sort of through which the planet is partially transparent and you're inducing absorption of the starlight, that annulus is defined by the planetary scale height, which depends on the mean molecular weight. So for a very dense atmosphere, like if you imagine an atmosphere of pure CO2, for example, which has this really high mean molecular weight, then the annulus through which starlight can pass is going to be very compressed because of the decreased scale height. Whereas for something where, if we go back to this case, if the planetary atmosphere has a metallicity of about 100 times solar, which is a mean molecular weight around 4 to 5, in this case, you get absorption through this kind of puffier atmosphere. And so it induces these larger features, molecular absorption features in transmission. And so when I'm showing these parameter space sweeps, I'm basically saying anything in this darker region we're excluding because it would induce features large enough that we could see it. So one thing that we've been thinking a lot about is our spectra, we think, are flat. I guess I'll just go here. But TOI 270d and K218b are these other sub-Neptunes that are non-flat. They have features, absorption features in their atmosphere. Something that we think might be happening is potentially there's a dependence on the equilibrium temperature. So there are a couple of papers about this. I've taken one from Yoni Brandy's paper earlier this year and reproduced it just to draw on the equilibrium temperatures of the compass targets. These aren't the actual feature heights that we measure. I didn't include those because it's not a one-to-one comparison, because Yoni's work uses the water feature amplitude in the Hubble bandpass, but like I said, our observations don't have a complete water feature. But just schematically, you can see that if it's the case that this kind of parabolic relationship with temperature bears out, then we might be, we might unfortunately be in a regime where our planets mostly don't have features. The reason this is thought or hypothesized to occur is that the coolest planets can really efficiently remove haze particles from the atmosphere. And then the warmest, important haze precursors don't exist in the atmosphere. In particular, methane starts to disappear around 700K-ish in thermochemical equilibrium. And so if you're getting rid of all your methane, then you don't have anything to make the haze that obscures the atmosphere. Except very recently, GJ9827d, which is a planet about 2 Earth radii, so another sub-Neptune. It's this one in Yoni's paper where the error bars are fairly large, so you could imagine maybe there's some kind of with the Hubble data, maybe there was just something, some systematic error with the measurement. But this planet is at 600K, so really right at the bottom, the trough of the parabola. But JWST nearest appears to show absorption features. So I was not involved with this work, but I like their plot, so I've just plopped it on here. This is from Carolyn Pialegoriev. And you can see, it's no WASP-39, but there does appear to be molecular absorption in this atmosphere. They run a retrieval and show that the water component is probably about 50% of the atmosphere, possibly even more. So it's a water-dominated planetary atmosphere. So this is a very schematic plot. It's based on a very simple assumption that planetary composition varies only with radius. Like, don't tell Natalie that I'm showing this plot. But just very schematically, right? If we're trying to understand why why some of these planets have features that the compass targets don't, I think it's instructive to look at this kind of stellar radius versus the planetary radius plot, where you can see that sub-Neptunes like K218b, TOI 270d, they have a small host star, probably a reasonably puffy primary atmosphere. Great, you can observe them. As you go to smaller planets like GJ9827d, which appears to have this water-dominated atmosphere, it could be the case that the compass targets in that part of parameter space, because we have this bandpass where there isn't a lot of water absorption, if water is the dominant absorber in the atmosphere, maybe we actually need to be looking at these planets with a different instrument in a different wavelength regime where we can get more water absorption. And then for the rest of the compass targets, perhaps for our other sub-Neptunes, the star is a little bit too large, so that that annulus that I talked about for transmission spectra, the relative size of that compared to the stellar radius is too small, so it doesn't block out a large enough fraction of the light for us to see it. And then for these planets below the radius valley, maybe they're bare rocks, or they have like very thick, pure water atmospheres or pure CO2 atmospheres that can't be observed with current kind of, at least with current 1 to 2 transit technology. Maybe if we stack a bunch of transits over the lifetime of JWST, we can get down there. Okay, so to summarize my planet atmospheres work. So even with a really nice, allegedly easy mode, panchromatic hot Jupiter spectrum, we have more theoretical legwork to do to make sure that our models can generate consistent results. There's also still a need to sample widely across parameter space for small planets, since we don't know in advance which of them are going to show features, and we're really in the hunt for molecular absorption features because that's our clue to what the compositions of these atmospheres are. And then with a little bit more, inference, we can try to understand their structure and formation histories. And then we also potentially, modulo maybe some, depending on what you think of this parabola, at least so far, the coolest planets do have a pretty good hit rate for showing molecular features and absorption. So we probably need more planets like this and more planets around bright M dwarfs that are suitable for JWST, so that we can build up the sample of planets that have absorption features. Okay, since we're doing kind of more interactive, if people have any questions about that section, I'm happy to take them now. Okay, great. So I'll move on, kind of segueing from this need for more JWST accessible planets. I'm going to talk about some planet discovery work. So like I said, these low temperature planets, they probably aren't, oh, actually, I should have changed this line on the slide. They're certainly not the only ones that have features, but we've done pretty well with them so far. They're also, if you remember, intrinsically more common from the period radius plot I showed earlier. Up to at least 20 days, the underlying occurrence of planets is increasing, and then maybe not strong evidence for it increasing beyond that, but maybe by eye evidence. So these longer period planets are also more common. And so to really get a comprehensive understanding of the population, we want this representative sample, which needs to include the actual most common type of planet. Unfortunately, the current kind of premier planet finding instrument is not super well optimized for long periods. So for about 2/3 of the sky, TESS only has consecutive coverage for 28 days, and then it will have subsequent coverage like a year or 2 years later. And so if you imagine a planet with a period in the 20+ day range, you're most likely only going to get one transit per TESS sector, which leads to this big, a lot of period aliases that could be the planet's true period. So you have to do a lot of legwork. I'm going to skip some of the work that I did earlier in my thesis, and also a target that I worked on with an undergraduate student, Amanda Moore, who I had the privilege to mentor. These are both interesting systems, but for the purposes of this talk, I don't think there's time to discuss them, although feel free to ask me after. And instead, I'll focus on the multi-planet system TOI 4353. So representative of the kind of TESS long period issues that I was talking about. So I found this when I was my second year in grad school. JWST hadn't launched, and Natalie was like, do you want to, come up with something to do? So I started searching for long period planets in TESS. And this was one of the targets that jumped out from my search. It has these 2 transits that are 2 years apart with no phase coverage in between. So a lot of aliases are possible. Before we go hunting for aliases, though, we probably want to confirm that this is a real transit. Since it's a small object, it's kind of moderate SNR, so we want to be sure we're not just like going on a wild goose chase. I just stole this plot from one of the proposals I wrote for this target, where here's the period, and then you can see the test light curve showing the phase coverage that we do have, and then integer fractions of the 718-day period are shown in these red dots. The probability of those periods is calculated based on the transit duration. So at longer periods, planets have longer transits. And so, we thought it was probably one of these shorter periods. So first of all, we did confirm that it's transiting. We got this light curve with CHAOPS, which is the Characterizing Exoplanet Satellite, which is a European mission. Great mission, by the way, especially for early career scientists. It's not quite undersubscribed, but I think if you have a compelling target, it's not that painful to get a proposal accepted, get some photometry time, really good for bright stars. So CHAOPS, great mission, recommend. So we confirm that the planet is transiting. I have these little green dots showing the expected transit time, and you can see that it's offset a little bit, potentially suggestive of some transit timing variations, which in turn is suggestive that this might be a multi-planet system. Oh, sorry. So do you mean the likelihood for aliases in DDT? Sorry, yeah. So this is just that's the director's discretionary time, which was the format for which we submitted this proposal. So it's
PPT.
Oh, sorry, the flux. Oh, yes, I'm sorry. That's just parts per thousand. Yeah. Sorry about that. I thought you said DDT. Yes, parts per thousand. So this is the normalized light curve. So the relative, so it's about 1 part per thousand transit, or 1,000 ppm if you think in ppm. So we went off on this alias search and didn't find anything. I think this is actually, in as much as somebody who's still a grad student can have wisdom to impart, I think this is something that I wish I could go back to my younger self and say, you already have evidence for TTVs, so you should get a longer baseline of your transits, because some of these alias searches are actually not very constraining. So you can see that the phase is in days, so 0.1 days, about 2 hours. We have like 45-minute to 90-minute, depending on model assumptions, transit timing variation, and just the first 3 transits. So probably should have searched a little bit more widely with this initial alias search. One thing we did find is we think we saw the ingress of another planet. So these data were obtained last year. I actually don't show the expected transit time, but this is about 5 hours off from when the original planet should transit. So that's getting to the point where invoking 5-hour TTVs is maybe a little bit dicey, not impossible, but additionally, when you fit the transit depth, you find that it's distinguishable from the initial 3, which were all consistent with each other. So this is suggestive that this is a multi-planet system. That suggestion is further enhanced by some radial velocity data that another team took. They asked me not to show their data in talks, so I don't actually have it, but I will tell you that with Espresso, which is a great radial velocity instrument, kind of top of the line, there's very strong suggestion of at least 2 signals, and then kind of hints of a third that might be the stellar rotation period, maybe it's an outer planet. So we feel pretty confident in saying this is a multi-planet system. Hot off the presses, we thought we knew the period from these RV measurements, but over the weekend, we got some new data, and it doesn't have a transit in it. So I was kind of hoping that I would come into this talk like triumphant, like, ha, we've solved the system. But we actually have a little bit more work to do, which a little bit deflating. I think this is still a very exciting system. More observations are kind of in the pipeline. Ground-based follow-up is ongoing. So it kind of goes to show that this this follow-up of long period planets from TESS is pretty challenging. It does require a lot of follow-up, but the rewards are potentially huge. So this is a very bright star. The smaller planet has a radius 1.4 Earth radii, and is sort of, if you know, based on its transmission spectroscopy metric, which is kind of a widely used, although not perfect, proxy for how observable a planet is, it's almost as observable as the TRAPPIST planets because the star is brighter. About 70% of the transmission spectroscopy metric of TRAPPIST. So this is potentially a really exciting system. This 2 Earth radius planet also has the potential, obviously we need to measure its mass, do a lot more follow-up, but could become one of these like kind of keystone sub-Neptunes that are great for observation. So obviously putting the cart before the horse a little bit, we haven't actually finished characterizing this system, but someday, maybe in the next KOPS cycle, we will actually wrap up this project. I originally had written look out for the paper, but don't hold your breath, might be next year, late next year. Yes. Oh, yes, sorry, HC is habitable zone. In this plot, I actually didn't talk about it, but the inner edge of the habitable zone for the star is around 26 days. And we think both of the planets have periods greater than 26 days based on our alias search. So they're both probably quite cool, which is neat, both for habitability and just for like their stability. Yes. Go for it.
Transit model looks to me to be kind of asymmetric.
Yes, that's just a byproduct of the plotting. So it's just like drawing a straight line between the last point here and the first point there. So the transit model isn't actually asymmetric. Yeah, I should probably fix that by doing just like a nice grid of times instead of just the data grid of times. But yeah, good question though. Yeah. Okay. Oh, yes.
Like your copy. The histogram of this planet detection, which is takes around 1.5 or so Earth radius, right? This one.
Yes.
And you also said that TESS has some observational bias towards some specific period of the planets, like 26 days or something like that, because of the coverage.
Yes, right. So a single.
Or will the period of the planet to the radius from the planet formation history?
Oh, that's a great question. I suspect that the answer is yes, but I would say that I don't think planet formation models as they exist are sufficiently well constrained that we could use that information to constrain this search, if that makes sense. Like, I think like if you could know nature perfectly, the question, are orbital period and planet radius linked, is probably yes. But I think our knowledge of that is sufficiently imperfect that we can't really utilize it to plan these observations. Does that make sense?
I just wanted to ask that.
Okay. Yeah.
Since you stopped anyway, can I just nitpick? Is this the full chaos folded data?
No, there are a couple more baseline sectors on either side. I just zoomed in on the transit. I think there are
Yeah, but for the transit times, this is full folded data set.
They're not full, this is one visit.
this is one visit. Yeah.
This is one, because it looks like it is not even. So the other visits must be shallow.
Yes. So this is actually a joint fit to the KOPS and the test data.
Got it.
Yeah. that I'm showing here. And then for this histogram, we fit them individually. And they are consistent, but yeah. Yes. Yes.
Last year, I think something that do transit program. Is this target being learned about program, or is it within program? And so like, how is it?
Yes. So great question. So there's like a GTO team, guaranteed time team on KOPS that does duo transit observations. So Hugh is actually on this proposal, and he had to get permission from the GTO team to be on this proposal to avoid conflict of interest. Basically, the science case for the GTO duo transit program is more focused on deeper transits, which might have been kind of smart, but too late now. Yeah, so this is a different science case. So this is all community time that I have acquired by applying for KOPS time, not from a GTO program. But yeah, their GTO duo transit stuff is also very exciting. They do really great stuff. Okay, anything else? What time are we at? Oh, it's 1 p.m. Okay. Let's see. I was told that we want to leave time for questions.
Yeah, we should wrap up by 1:15.
Okay, great. So I'll zoom through this atmospheric modeling stuff a little bit, just so that we can have time for a lively discussion. Someday in the future, maybe in 20 years, we're going to have this big library of very precise, hopefully, transmission spectra for small exoplanets. And I'm very interested in thinking about, when we have this sample, what will we be able to learn about the population from it? So that's kind of the motivation for this project, where I use a general circulation model to think about whether we can demarcate different rotation regimes with transmission spectra. So the motivation here is that planets around K and M type host stars are probably synchronous rotators, where they have one side of the planet facing the star at all times, except, especially in multi-planet systems, dynamical effects can really perturb them from synchronous rotation. You can discern dynamical regimes by phase curve, but phase curves are very observationally expensive. You have to stare at the planet for its entire orbit. They're also just not always possible. And so I was interested in thinking about, could we learn about the rotation regime of a planet by its transmission spectrum only? So to test this, we use Rocky 3D, which is a general circulation model. We do this parameter space sweep across irradiation and rotation regime, where we have synchronous rotators and then one-day rotators, which don't fully capture the dynamical complexity of the kind of like breaking of synchronous rotation. But for a parameter space sweep, it was, I think, a little bit, I think it was well motivated to test kind of this end member simple case, rather than doing a fully coupled climate dynamical simulation when you're not even sure if the effect is observable. So we're really just looking for, can we see in transmission differences between these cases? So the details of the planet, we have a fairly dry realization of this kind of representative super Earth, L9859d. I have here just kind of diagnostically the surface temperature and wind speed maps for the one-day rotator and the synchronous rotator, just to kind of orient your intuition that the one-day rotators are dominated by latitudinal variation, and the synchronous rotators are dominated by day to night side variation, because they have one side always facing the star. So the kind of takeaway from this project is there are some differences in the transmission spectra. So for each of our irradiation cases, I'm showing the transmission spectrum that we generate for the synchronous and one-day rotators. You can see that in the hottest cases, all the transmission spectra pretty much look the same. But for some of these intermediate cases, there is variation between the two cases. This effect is primarily due to clouds. So the zoom bar blocking my text. Let's see. Here we go. I'll put this over here for now. Oh, what have I done? Disaster. Okay, no, we're back. So in this case, I have removed the effect of clouds when calculating the transmission spectrum. This is not the same as doing a cloud-free simulation because clouds still have climate feedback impact. So this is just testing basically the optical effect of clouds on the transmission spectrum to show that most of the differences we're seeing are due to clouds. And you can kind of tell this intuitively, right? In the case where the difference is the biggest, you can tell that it's mostly a continuum difference, which is probably a cloud difference. So yeah. So we have a case where there's a 1D rotator where 1-day rotator where the rotation period of the planet is 1 day. And then we have a synchronous rotator where the rotation period of the planet is also its orbital period. And so, and we calculate the orbital period self-consistently with the irradiation. So in these hotter cases, the rotation period is actually getting shorter because the planet is moving closer to the star.
Two cases have the same orbital period?
Yes, for each individual irradiation case, they have the same orbital period, yes. There are some differences. When we think about why this is happening, these warm kind of 1.3, 1.6 times Earth insolation cases, they have these high altitude tenuous cloud decks that live right at the terminator. So in these plots, I'm showing the longitude marginalized cloud top height. The thickness of the lines indicates the average cloud cover, average across all cells in the simulation. And you can see that for the synchronous rotators, as you warm up above Earth insolation, you get these clouds that are quite high up, but they're quite tenuous. It turns out that they hang out right at the terminator, and this is what's driving, especially in this top right case, you can see there's this really big jump from the clouds, and that's because of these super high altitude cloud effects. Whereas the 1-day cases have these somewhat more stable, less tenuous clouds. And I have, if we want to talk in more detail about this, I have some bonus slides about more details of the GCM simulation. So preliminarily, this is evidence that transmission spectra could discern between rotation regimes. There are, I think, a lot of important caveats here. I'm not saying that I'm going to write a cycle 5 proposal like, I'm going to determine the rotation regime of this planet. So because the differences are driven by clouds, it's really important that we do confirmation work with other GCMs because each model parameterizes clouds a little bit differently. And people have variously done work in the past to show that that parameterization impacts the overall cloudiness of the simulation. So certainly, we would want to test this with other models. The effect is also relatively small. I didn't really say this, but you may have noticed that this transit depth of tens of ppm, with the differences between spectra being maybe at most 20 ppm, which is kind of the JWST noise floor. This is something where this might be observable when we have like in 20 years, kind of an end of life JWST really precise library of transmission spectra. I'll also note that it could be degenerate with other climate effects that promote or inhibit cloud formation. So I think it's something that you might observe at a population level where you look at all multi-planet spectra or sorry, spectra of planets in multi-planet systems to sort of assess is there are they more inclined to display this cloud behavior and hence this climate behavior because they're being broken out of synchronous rotation. Okay, so that's everything that's actually in my talk. I'll leave up some summary slides. I have my 2 papers that I managed to finish just in the nick of time before postdoc applications were due. For some QR codes if you want to check those out. And yeah, I'd love to have some more discussion.
Presentation. I wonder if, though time I know is very precious, I wonder if you could please perhaps chat amongst yourselves for 60 seconds before asking Nicholas a question. I find this is a good time for you to say, like, was this confusing for you too? And then one of you could work up a brain to ask that question. So,
Okay.
60 seconds. You get to breathe first.
De-sweater as well. I realized that the interior climate control is very effective.
Yes. And I always find just from teaching that,
Yeah. Yeah. I gave a guest lecture in Jonathan's class that I'm TAing for this quarter. And yeah, 90 minutes of just like, okay, so talking is hard work. Yeah.
I realize what I'm about. I heard the second order. I think it's not even the first order effect. It's acceptable, but nonetheless, because sometimes it was the effect, and then in fact, the symmetries are the morning and night turning into asymmetric GCM.
Yes, great question, and they definitely are. So this is actually I think who led this paper? It wasn't Tama. Oh my gosh, I'm blanking on whose paper it was, but there was a paper recently where that suggested specifically for a very different case than ours. It was examining kind of the ability of clouds to condense out if you do like a hot start. They found that there's this this morning terminator cloud that really like sits there. And we actually observed something very similar in our simulation. So yes, it is, like you said, it's a second order effect when the first order effect is already kind of dicey. But in the limit of like arbitrarily precise spectra, it's definitely the case that the morning and evening terminators are different. Yeah,
sometimes like English, get rid of systematic, actually pull out things that you couldn't see.
Yeah.
You wouldn't expect to see.
Right. Yeah. So I think for the small planets that we're thinking about, I don't think the precision is quite there yet. But definitely, something we're thinking about. Yeah, great question.
Beautiful. Thank you.
Oh, thank you so much. Oh, I'm so glad. Thank you so much.
Other questions?
Thank you.
So last thing on the
Yeah. Are you thinking about this?
Like this on that.
Yeah.
Oh, yes. Oh, sorry. Yes, the map. Yes.
On the red plot. Is that like synchronous rotator?
No, so all of these planets have an atmosphere. Yeah. So the GCM setup basically is because Rocky 3D kind of evolved from these Earth models, it's actually a fairly Earth-like atmosphere. So it's 1-bar atmospheres with mostly nitrogen, and then the radiatively relevant species are 400 ppm CO2 and variable amounts of water, kind of depending on the climate details. And the initial water inventory is basically like a layer of wet soil. So there's no global ocean, which we do in part because going up to 4.5 times Earth irradiation, if you have a global ocean, it tends to turn into a runaway greenhouse and break the simulation. So we deliberately have slightly or fairly dry planets. I think there's some level of physical motivation for that, in that the M-dwarf planets might lose a lot of their water, and so they might not actually have large water inventories. But yeah, so those are the assumptions that are going into the simulation. So there is an atmosphere and there is heat redistribution, but it's not efficient enough to overcome like the staring sun. Yeah, great question. Yes. Okay, so this is planet D, not planet C. Planet C is even hotter in the L9859 system. Planet D, actually, Zach and I were just talking about this. There is a transmission spectrum of that planet that was published recently that reports finding a hydrogen sulfide dominated atmosphere, which is very weird. And that paper, it's seemingly at least somewhat dependent on reduction technique, which is a little bit eyebrow raising. So if you believe the hydrogen sulfide atmosphere, this is certainly not consistent with that. But if you think that the atmosphere that they're seeing is probably actually, or the absorption that they're seeing is probably systematic effects, and the spectrum is flat, then this is perfectly consistent, because these absorption features are kind of like not really observable with one JWST transit. But yeah, great question. Yes.
Yeah, I thought this is a great talk, and I had a couple questions about this too.
Okay.
I mean, I think this is really neat, but so my first question is like, is there a qualitative reason why there's a cooler spot right in the middle where I expect it to be hotter, like right in this synchronous rotator one? It dips.
Yes. So I believe what's going on here is you're seeing the effect of this. So actually the cloud deck plot kind of has it. So you have this really high altitude, well, in the cooler case, it's not as high altitude, but it's still fairly high up. You have this cloud deck that sits at the substellar point and dramatically increases the albedo at that point. And so this plot actually, this paper is still in review, and actually the referee pointed something out about this, but this plot is kind of ironic because we're doing these 3D simulations, and then I'm showing all these like 1 and 2D plots. So they were like, you should show these in more dimensions. So something that this plot is missing is that the thickness of the cloud deck isn't the same. And so it's the most cells are covered by the cloud deck, like at the substellar point. And so what you're seeing in the temperature here is that it's slightly cooler right at the substellar point because of this really thick cloud deck. And the cloud deck thins a little bit beyond the substellar point,
Wow.
I think. Yes.
So just related to that, and you don't see a fact in simulations of this offset of the hotspot from the substellar point.
I don't think so. Yeah, I don't think so. Definitely like, I'm seriously trying to think, because certainly for like hot Jupiters and hot Neptunes, you do see this offset, and I'm trying to think if there's some assumption, there's some assumption that we're making in our simulation that causes that to not appear, or if it's just an artifact of having this relatively thin atmosphere that isn't as efficient at redistributing, and slower rotation as well.
I hear what you're saying. It sounds like you need to think about it a little more, but even a solid planet, finite thermal inertia, with no atoms, the hottest part point of not being substance study.
Hmm.
Because planet rotates, has some kind of inertia.
This planet doesn't rotate.
It does rotate, rotates in the same speed as it.
Yeah, yeah, it is physically rotating, right? It's,
Yes.
yeah, no, that's,
Wow.
yeah,
Do you think? Yeah.
okay. Thank you for the save, Zach. Yeah,
Thunder.
yeah, sorry, so great question. Okay, sorry, people on Zoom, I have, oh no, I got rid of it, never mind. So the substellar point, for a synchronous rotator, because you have one side of the planet always staring at the star, there's a point on the planet which is the closest to the star at all times. And so that's the substellar point. It's just the part of the planet that is directly, I mean, maybe it's not quite correct to say it's receiving the brunt of the stellar radiation, but it's the point that is at sort of closest to the star. Yeah.
What is it not centered about?
Right. So I think the point that I'm sorry, what's your name? What is it?
Odette.
Oh, that okay, is making is that so as a planet rotates, so if you think about like an instant snapshot, the part of the planet that's receiving the most heat is going to be the substellar point, but the planet is rotating, and so when you observe it as it's re-radiating, the hottest part will actually be slightly offset from the substellar point.
And for planets with atmosphere, it's actually being observed.
Yeah.
That winds carry the heat away from the place that we see radiation.
Yeah.
And Zach, you're right, for solid planets, there is no effect except there's an explicit.
Yeah, these are zero eccentricity simulations. Of course, yeah, great question. Sorry, I was throwing around terms with that explanation.
We've gone way over. So we just,
Sorry.
let's take the first one.
Thank you so much for the discussion, Charles. All right, thanks everyone on Zoom. Thank you so much for coming.